Hey, amazing. So, hi everyone. Today we'll be talking about 3D Gaussian splatting. Here's a little demo of what you will be working at for your next homework assignment once we put it out. It's going to be a very simplified version of putting 2D Gaussians to fit a 2D image. And today, we'll kind of take 2 steps back and talk about differential models in computer graphics and just how we've been representing our real world so far, recap a bit of NeRFs, and then tune into 3D Gaussian splattings, talk about what does it even mean to have a 3D Gaussian splat somewhere floating around in space, and then have an overview of the pipeline of 3D Gaussian splatting. How do we initialize this model of our scene, and then how do we render it out, how do we optimize it, and then we'll talk about some exciting recent improvements at the end. And if you have any questions, feel free to stop me anytime. So if something is not clear or if something is too quick and like to learn more about it, then just feel free to let me know. So differentiable models in computer graphics, the big picture is that we have our real world. For example, we have a tree somewhere floating around in space. We look out our window, we see our tree. And in a sense, some photons hit our eyes that make us see a tree. And in computer graphics and computer vision, we essentially want to come up with numbers that kind of describe a model of this real world so that we can virtualize this whole thing. And we can think of these parameters, these numbers, as kind of knobs that we can tune that kind of let us, using the same model, let us describe different things in the world, whether that be a tree or something completely different. And so far, we've been looking at triangles, which is kind of the very original way of computer graphics, the most established way. We've been looking at kind of these numbers being the weights of a multi-layer perceptron, describing a NeRF, and rendering stuff out as a volumetric box. And today, we'll be looking at these numbers describing ellipsoids floating in space, 3D Gaussians, that we can ray trace through, which will pretty much mean that we will bring an alpha blending of these view space ellipses. And then once we have our model, naturally, we want to render it out, so measure our virtual world. And in theory, if we did everything right, then if you replace our window of the real world with our computer screen, kind of our perfect case would be that the same photons hit our eyes and we don't even notice the difference between the real world and our virtual world. But of course, this is not the case. We want the observation to be the same, but it won't be perfect. So we have to come up with a measure of how do we measure the difference between our virtual world and our real world. And then we would like to tweak our parameters for better results. And this is what we've been doing when we were optimizing some neural radiance field and tweaking the parameters of our neural network. And this is exactly what we will be doing with 3D Gaussian splattings, but our parametrization will be a completely different concept. I'm not sure if we mentioned this specific expression, but a very established and important problem in 3D computer vision is novel view synthesis, and NeRF proposes a solution to this. For example, we have our nice bulldozer in the middle, and we go around it, taking pictures of it from different angles, and we end up with some, for example, RGB images from different directions. And the novel view synthesis problem is that we would like to reconstruct a view from a completely different angle, which was not part of our observation set. And kind of the idea here is that given our camera positions and given our observed images, we would like to construct some kind of model of our 3D space. And from this model, we would like to sample or render out this model from a different viewpoint. And ideally, this should be the same as if we just took a picture from that angle as well. So just to recap, with NeRFs, we've had a neural network, an MLP, taking some X, Y, Z positions in 3D space and also some view direction. So it mapped this 5D space through an MLP. and into some 4-dimensional RGB and sigma density vector, which was a because neural networks are give us a continuous function. We essentially, when we were sampling array to render out our image, we essentially had to sample a continuous function. And if you remember your homework, you essentially implemented ray marching through this ray to essentially integrate this continuous function along this ray. And once we integrate this ray along our, once we integrate this color density function along our ray, we get one single RGB pixel color at any pixel value. And then we would like to compare this with our ground truth color. We take, for example, the squared L2 loss, and then we take the derivative with respect to the MLP parameters, and we do some gradient descent-based iterative stepping to find some minimum of these losses. What I would like to highlight here is that we had to do an expensive ray marching because we simply didn't know where we have some density and where we have no density in our function essentially. And this was NeRF in a nutshell. And of course, the question also arises whether expensive neural network is actually worth it. If you remember, we mentioned planoxels, for example, that completely gets rid of neural networks and just tweak parameters on a grid. And this will be a kind of a thought that arises also in 3D Gaussians. But I think whether we actually need this this whole expensive neural network parametrization. And then, of course, the iterative training function was that we just come up with some random initial parameters, so some random initial parameters of our neural network, and then we keep doing some gradient descent-based iteration, and we keep getting better and better results while we were tweaking our little parameters, our weights of the neural network in this case. And this is, in a sense, the heart of all differentiable rendering. That this is kind of the big picture of differentiable rendering. Then once again, maybe we were walking around campus and we saw Buzz dancing around somewhere on campus, and we took a picture of him. For example, that resulted in, for example, a 512 by 512 RGB image. And very simply, and I think this came up in a previous lecture, that we can do like a NeRF style learning or overfitting to a single 2D image where we directly learn each RGB image for each pixel. So we essentially just map an XY pixel to an RGB color with a neural network, with an MLP. And then this is that learning process. Or with our Gaussian splatting discretization, we initialize some points in 2D space in this example with some stretch along the one axis and the other axis, and probably maybe also some rotation. And then we blend these together to come up with an image, and we just keep trying to find better and better parameters for our Gaussians. And we might, because this is a particle-based discretization, which means that instead of some implicit description from the neural network, we have some explicit particle positions. We might also come up with some ways to prune or densify, so to have less particles or more particles at areas that might be higher or lower detail density. And it's best to show you an example. And because live demos always work so well, I thought of just showing you nice visualization here. This is running live in a browser, and this is a 3D Gaussian splatting model of a radio tower in San Francisco. And one of the very cool things about 3D Gaussian splatting is that it kind of it achieves up to 100+ frames per second in real time, and also has, I think, amazing quality. And kind of what I want to show you is that if we break this, and of course you can play around with this at home, but what I want to show you is we kind of break the illusion and we kind of zoom in. That usually, if you zoom into a usual 3D model, you end up seeing like some triangles in the end, usually. Like that's kind of the the established way of doing stuff. But if you keep zooming in to some 3D Gaussian splatting model, you end up seeing these 2D Gaussians, these ovals, essentially, instead of pixels or triangles. So in a sense, we have these 2D screen space Gaussians, and we blend these together to get our view. And the paper was published at SIGGRAPH 2023, 3D Gaussian splatting for real-time radiance field rendering. And this is one of their results that they show in their paper. And this is rendered in real time, I think 60 or 100 FPS or so. And this is essentially hundreds of thousands, if not millions, of little Gaussian particles floating around in space. And you can also notice just how crisp the details are on the bicycle and all around. So leading into 3D Gaussian splatting, the image formation model is actually going to be pretty much the same as NeRF's, because NeRF had a kind of differentiable volume rendering, which is kind of similar to alpha blending, whereas I already mentioned that with NeRFs, you had to integrate this continuous function with ray marching, which was a kind of differentiable volume rendering of some continuous description. Whereas with Gaussian splatting, I already started hinting at this being a particle-based discretization, which means that once you have, for example, if your camera is looking from this direction, and you want to calculate the pixel value for this pixel, for example, then actually you have a discrete description of where your contributions are. And as you're integrating along this ray in either direction, you don't have to do your expensive ray marching, but you can essentially just take the contribution from this green splat, from this blue splat, and then this red splat along your ray. And they also do a lot of very fancy GPU implementations to make this extremely efficient on the GPU with some custom CUDA kernels. And as an overview of the 3D Gaussian splatting pipeline, the first question that we'll answer in the next part is, what are 3D Gaussian splats anyways, and what does it mean to parameterize the 3D Gaussian splat? And of course, we also talk about how we initialize these and what a structure from motion point cloud is. And once we have our initial set of 3D Gaussians and their parametrization, we want to take some camera position and camera angle and project our 3D Gaussians into our 3D Gaussians from our workspace into our 2D Gaussians in screen space to essentially get 2D screen space Gaussians like this. And then once we have these 2D Gaussians in screen space, we render out our projected Gaussians using alpha blending. And once we rendered out our image, we want to compare this with some image as exactly the same way as we did with NeRFs. We come up with some loss function, and using this loss function, we take its gradient with respect to our Gaussian parameters, and our gradient flows through our pipeline with the added extra bullet point that, as I already mentioned, we might want to increase or decrease the number of Gaussians, because if some parts of the picture or the 3D scene is very intricate, then we might want to put more Gaussians there. If you have some empty space, then one of the benefits of Gaussian splats is that we don't have to put any points there. Whereas with NeRF, we kind of had to dedicate some memory to empty space. And kind of the whole projection, rendering, alpha blending part, and the whole making it differentiable part will answer the question of why would we really consider using 3D Gaussian splats. But before we dive into that, let's answer the question, what are these 3D Gaussians anyway, and how could we parameterize these? So the easiest example is a 1D unit Gaussian, where you have some x-axis and you have a 1D function describing some y coordinate for each x value, where you have a unit Gaussian centered at 0, and it has some unit variance. If we let it have some different center and also have some different standard deviation, then we end up with our 1D Gaussian function, where we can notice that there's a scaling factor along the y-axis, which makes it integrate to 1 over our axis, which makes it a probability density function. And if we just let our center and variance vary, then we can describe different PDFs with this. But actually, if we just don't integrate to 1 over our domain, but instead we just let the scaling factor vary, then we can just use some coefficient C that we can just where we can just change the position of our Gaussian. We can change the coefficient of the Gaussian so that it no longer integrates to 1, and then we can also change the scale of our 1D Gaussian. And essentially, this is what we would like to bring up to higher dimensions. For a 2D Gaussian, so starting from our 1D Gaussian with some x position and some single scale. In 2D, we want to have an x and a y position or center or mean, and also some scale along the x and y axes. And we also want to have some rotation, which we can just describe with a single angle in 2D, for example. And then the generalization of our Gaussian function becomes this exponential term, where we have some displacement of our input coordinate to have our Gaussian centered not at the origin, and then kind of the generalization of dividing by our scale becomes the covariance matrix, which is a concept in probability theory that kind of generalizes the notion of having some variance along multiple directions. Where if we have values of our 2x2 covariance matrix only along the main diagonal, for example, here I'm plotting just having 1, 1 over our main diagonal. Then we have some isotropic Gaussian, where isotropic means that it's the same along all. It has the same scale along all dimensions. Whereas here I changed the scale to 0.3 and 2, where we see that it stretched, it pushed together the Gaussian along one axis and stretched it along the other. And the other parts of this 2D covariance matrix is kind of a measure of how much the different angles influence each other. And something we need to be aware of, that of course we could just say that, okay, then that's amazing, let's optimize for these 4 numbers in our covariance matrix because this describe some 2D Gaussian, or then the generalization into 3D will describe some 3D Gaussian. But actually we want this sigma matrix to be invertible. So we also want to make it symmetric. And to achieve this, oh yes, so here I'm just plotting, changing the center and the covariance matrix, just to show you that essentially a 2D Gaussian in x and y essentially gives us a height map or a single scalar value that we can think of as a height map. Or if we just look at it from top down, then here you can see that that this essentially goes from 0, the blue part, to 1, which is this middle part. And if we just multiply this scalar value by some color, for example 0, 0, 0, 1 for blue, then we get a 2D colorful splat in 2D space. But as I mentioned, so backtracking, we actually want this sigma matrix to be invertible. So we would like to parametrize this, not directly by the values of these matrix entries, but instead kind of building up this matrix from our scale and rotation by having this this is, I think this came up in computer graphics for sure, and I think maybe in this class as well, that you can just construct a 2x2 rotation matrix from a rotation angle, and you can also construct a 2x2 scale matrix from some x and y scale. And then this also lets us be very efficient in computing the inverse without having to resort to any typical inversion schemes. Where if we remember that there is that if A and B are two square matrices, then their inverse becomes B inverse and A inverse. And if we just apply that here, then we essentially have R transpose inverse, which has a very nice property because it's orthogonal, and rotation matrices have a very nice property that their inverse is also their transpose. So this essentially becomes R. R transpose inverse becomes R, and then we have the inverse of SST, which where our scale matrix also has a very nice property that it has values only along the main axis, as I'm showing here. So SST becomes SST inverse, and our R transpose matrix becomes, and the inverse of our rotation matrix becomes R transpose. And our rotation matrix in 2 dimension is this typical 2x2 rotation matrix. And you can see that this is, even though it's so the generalization of dividing in 1D by some scale, which is the square of our standard deviation. Oh, in probability theory, I actually get confused by this because some papers actually confuse this, but sigma stands for standard deviation in probability theory, and then sigma square stands for variance. And once you start talking about covariance matrices, but your sigma is actually being squared, then it becomes a bit blurry and it's easy to mess up. So I'm sorry from anyone if you notice me confusing the two, but I try not to. And once we constructed this matrix, then it becomes our SST inverse RT, or sigma inverse. And actually, this generalizes to 3D very easily. Where our sigma inverse matrix is constructed in exactly the same way, but now our scale matrix is a 3x3 matrix with values along the diagonal, and our rotation matrix is constructed from is a 3x3 matrix constructed from a quaternion, where we have some real part and 3 imaginary parts. And now we can once we optimize for our scale and rotation parameters, then we don't have to worry about our gradient descent iteration step, kind of throwing off our covariance matrix into a non-invertible state, for example. And it's a very nice way to just have a different parametrization of something and make it work for us. And also, there are 2 ways to introduce this, because this is a bit of probability theory, because you have this whole PDF notion, generalization into ND of a Gaussian. But actually, the computer graphics way is actually just telling us that we are actually just parametrizing an ellipsoid, where we have some scale along some local x-axis, along some local y-axis, and along some local z-axis, where this is some ellipsoid. And then we also have some rotation here. So that's the computer graphics way, that actually we're just parametrizing an ellipsoid. Okay, so now let's look at how we could initialize these parameters. Actually, random points are good enough, but there is an alternative method that we get for free during camera calibration. Did structure from motion come up in a previous lecture? Okay, so this is, I don't want to dive deep into this because this is a very established and and typical way in computer vision to calibrate camera poses, where I just want to stop this. This is a very cool paper project where they are building Rome in a single day. And what they did here is essentially take a bunch of images from the internet, I think from Flickr at the time. And then what they're doing here, this is a computer vision technique, is that they try to optimize for their camera position and orientation for each of these images. So you see these cameras scattered around the 3D space. These are all an image downloaded from the internet. And they're essentially optimizing for some camera translation and camera angle, which is called the extrinsic parameter of the camera, as well as they also have to optimize for something called the intrinsic parameters of the camera, which describes kind of the focal length and how a camera projects from 3D space into its view space in 2D. And they have to optimize for all of these parameters. And I'm just mentioning this because I think this is just fascinating, like how can you parameterize the same thing? Because you essentially have a translation matrix, an extrinsic matrix of the camera, but instead of that, you're doing pretty much the same thing as here, that you're optimizing for some XYZ translation from which you build some extrinsic matrix as well as some rotation. And you essentially construct extrinsic camera matrix that puts your camera in vert space where you want to put it. And of course, that's also the matrix that puts everything in vert space into the camera space. And then the projection matrix is the thing that projects from 3D space into 2D space. And once you have these, there are computer vision techniques to look for important points that match between different images. And then using the inverse of the projection matrix or something similar, they essentially shoot the pixels back from 2D image space to 3D space. And that's what they want to optimize for. That if you have a pixel in this image and this image that points back to the same 3D point in space, then once you apply once you put your camera in space and you invert your projection matrix, then the 3D position to which that pixel back projects to has to be the same than the pixel back projecting from the other camera. Does this kind of make sense? Just this in this hand wavy way, because I was very wary of, I didn't want to put all the equations here. But the whole point that I want to get across is that you end up with some, actually you kind of just want to optimize for your camera position, because all you care about is where my 2D images are in 3D space. But actually, in this process, you get something for free, which is this 3D point cloud, which you kind of just used as a byproduct of matching these different camera images between different camera positions and images. So this is kind of a quick bird's eye view of structure from motion. This is a very established 2D to 3D pipeline in computer vision, and we've been using this for I think like 20 years or something, and it's very typical. It's kind of slow. It's kind of not perfect, but it's like good enough, especially for closed scenes that are not incredibly big. Like, yeah, it couldn't handle, for example, like a citywide optimization, or with some caveats at least. But in any case, we input our 2D images, and they pulled 150,000 images in the example that I just showed you. And it outputs some 3D camera parameters. And if you remember your homework, the NeRF synthetic data set, that's exactly what you were playing around with. You have your 3D camera parameters, and structure from motion also outputs some sparse 3D point cloud, where sparse means that it's not dense. So you don't have a lot of, like it's not enough to cover all the geometry, because you have you only have the points that kind of match between different images. But what's cool that you also get color for free, because as I mentioned, you were back projecting your 2D pixels into 3D space, which means that you get not just the 3D XYZ position, but also color for free. And call map is the go-to implementation. If you just go around your room and take some images, you go to GitHub, to callmap.github.io, and just run callmap, then you will get a nice structure from motion implementation. But as I mentioned, we can just skip this whole part, and we can just initialize random points with random colors. And this might be handy if we through some magical reason, we already have our calibrated 3D cameras. Because, of course, if we just have our 2D images, then, of course, we have to run some camera calibration to get where our 2D images are. But if we have that for free, for example, through having a synthetic NeRF dataset, which they just rendered out in Blender, so they have ground truth camera positions and camera parameters, then we can just initialize with random points. And in 3D Gaussian splatting, they actually achieve a very high quality result with just completely random initialization. But it's slightly better to use the structure from motion sparse colored point cloud. So as I mentioned, to initialize 3D Gaussian splats, you either start from a sparse structure from motion point cloud or random, which doesn't give you any normal. So if you remember surfolds that came up in previous lectures, you had a notion of a normal for each surfold. We don't have a normal for 3D Gaussian splats. And they start with isotropic Gaussians, which simply means that they have the same scale along each dimension. Whereas anisotropic means that it varies depending on which way you're coming at it. And then during the optimization, and something I'm kind of glossing over is that they are not just using an RGB color, but they're actually using something called spherical harmonics that already came up in previous lectures. But because of some optimization details, if you just so spherical harmonics in general are a nice way to represent a view-dependent color, which is exactly what they use it for. And if you look at their implementation, you literally have a function that's called sh to RGB, and you just have to give it some view direction, which simply converts some 16 numbers or so, your spherical harmonic coefficients, into an RGB color given some view. And the zero-order spherical harmonics actually don't depend on the view. They are the diffuse or base color. And this is what they start optimizing for, just to get the diffuse color right, because they noticed that during optimization, if they just throw all of the spherical harmonic coefficients to the optimizer at once, the optimizer might start fitting these higher order spherical harmonic components and kind of miss out on the diffuse part, especially if we have some weird, like for example, like the side of our scene where we don't have a good closure from all the images. So if we have the side of our scene and we have just a couple images from some weird angles, then it might completely do some weird stuff with the view-dependent colors. So they just start optimizing for the diffuse color, which is the zero-order spherical harmonic component, and then they introduce a new band every 1,000 iterations. And I'm not sure how much you went into this in previous lectures, because I saw that it kind of came up. But essentially, like for our purposes, it's essentially just a way to describe a view-dependent color. Whereas with an RGB, because if we had just an RGB color, then we would be missing out on specular details, for example. Because if you think of a mirror, for example, or a shiny car, naturally, given some XYZ coordinate, we have a different color based on where we're looking at it. And this was the same with NeRF. So if you remember, you had to input your XYZ coordinate, but also your view, your two view angles to describe your spherical coordinates on a sphere. And actually, spherical harmonics are essentially like very similar to the notion of Fourier transform and Fourier functions, because the way I understand them is that you have your sines and cosines in Fourier space of your basis functions in Fourier space are essentially sines and cosines of different spatial frequency. And then the most important part is that they span your domain, which means that they span the space of functions, of all possible functions that you can have on that domain. And then you can just take some linear combination of your Fourier basis functions to give you any functions. And then you can, and it's enough to keep note of how much am I taking from this sign and of each different frequency. And you have to truncate your Fourier space at after some n Fourier basis. And it's very similar in spherical harmonics, but actually your functions, your spherical harmonic functions, span all functions defined on the surface of a sphere. And you can take some linear combination of these functions to describe a function, describe on the surface of a sphere, which is exactly what you need for some view-dependent color, because if you look at it from this angle or this angle, that's essentially given by some spherical coordinates, so some one axis and the other axis. So this is a high-level overview, and they use the first 16 spherical harmonic coefficients, which can be visualized in many ways, 2 of which can be seen here. So just to tie it together, we can parameterize a 3D Gaussian, which is essentially an ellipsoid in 3D space, with some XYZ position and also a scaling along one axis, the other axis, and the third axis, and also some rotation, which is given by a quaternion. So 4 more numbers. And we also add in a transparency, which tells us how much can we see through our 3D Gaussian, and the color is given as 16 numbers, which are spherical harmonic coefficients. But for our purposes, it's enough to think of that as an RGB color that's view dependent, because spherical harmonic coefficients are just a parametrization for an RGB color, which we actually want to get to in 3D Gaussian splatting. And as I mentioned, once we have our 3D Gaussian splats floating around in 3D space, there's an efficient way to project these 3D Gaussians into 2D view space, in 2D camera space, based on our view. And as I already mentioned before, each of these Gaussians are essentially a scalar function in view space or in camera space. And the main point is that this 3D to 2D projection is very efficient because usually there's a matrix that works for us in computer graphics to change our perspective about stuff. And in this case, starting from our 3x3 covariance matrix, we can apply some view transformation, which is the camera transform of the view transform of our camera, which comes from the extrinsic parameters, as I mentioned before, which kind of shifts the whole 3D space into our camera's view. That's the V transpose and V transforms, and then we have a projection transformation, which but we actually have to approximate this because it's a nonlinear operation to apply a 3D projective transform. So this is the Jacobian of the affine approximation of the projective transformation, which essentially warps the 3D space into 2D space. And these are just matrices that you can look up, and based on the extrinsic camera parameters, so where you put your camera and how you angle it, and the intrinsic parameters such as the focal length and essentially how that camera projects the 3D space into 2D space, which is described by these Jacobian matrices. And actually, if you are curious about this, you can look up this paper which describes this in detail. It's actually quite cool. They have some cool visualization of how they approximate the whole 3D projection. And it's very funny because actually this came out in 2001, and something I wasn't sure where to plug in, but it's very funny that sometimes people keep mentioning that Gaussian splatting just took the world by storm and it came out of nowhere, and it really didn't. So everything that we're talking about here has been 20+ years in the making, and there are lots and lots and lots and lots of build-up to everything that's Gaussian splatting. But that's just a quick aside. So once we have our projection step, we essentially have 2D Gaussians in camera space, and we also have a z coordinate, which or the depth of our Gaussians. So this is essentially the x and y axis, our image coordinates essentially, and we also have a depth to our 2D Gaussian, like how do they stack up against each other, which one is in front of the other one. And essentially at each of these depth values, we have essentially a 2D Gaussian. And what we want to do when we rasterize or render out or alpha blend our scene is essentially alpha blend these layers together. And the rendering algorithm is essentially this, that for all pixels I, the I pixel of our image becomes the alpha blending of these 2D Gaussians, where where we input our pixel coordinate and also our Gaussian parameters as projected into the 2D camera space. And once we have this and we kind of change our perspective, then each ray becomes essentially something like this, where we have, where, as I mentioned already, but I just want to stress this because this is very cool, we have an explicit position for each of our contributions to our function that we want to integrate over. So, so if you remember doing your expensive ray marching in NeRF, for example, or if you think about if you had any kind of naive grid, for example, like some grid of values, we would also have to ray march through that unless we have some fancy acceleration data structure. But what's cool about this is that we know that, okay, at this z coordinate we have some contribution, at this coordinate we have some z contribution, and at this coordinate we have some contribution. And I'm pretty sure that this expression already came up before. This just describes alpha blending. And if you read the 3D Gaussian splatting paper, they actually describe how this is essentially the same image formation model as NeRFs, but kind of just changing up a couple of things where they have some density, where a density in NeRF describes how dense it is. So essentially, if you have some photons kind of going through it, then the density describes what percentage of those photons get lost, essentially. So for example, if a density is 0.6, then that means that 60% of your photons become color there for our purposes, and 40% kind of pass through that part. And that's what you did in volumetric ray marching, essentially. And this is the same concept, but opacity is kind of 1 minus transparency. So opacity means how opaque something is. So if this is, I don't know, like 0.4, then this just means that we have some opacity of 0.4, for example. And I might try out this fancy. Does this work? Oh no, okay. Okay, sorry. Okay, so if this red value has, for example, an opacity of 0.4, then we just multiply 100, which is RGB red, with 0.4, and then that's our contribution, this contribution for that red part. And when we get to the blue part, this portion is essentially just telling us how much the previous layers essentially took out of our photons, essentially, if you want to think in terms of that. So that means that 0.4 of light reaching our eyes was taken up by this red layer. So that means that 0.6 kept going. And for example, so this becomes, for example, 0.6%, sorry, 0.6, so 60% by the time we get to this blue layer, where, for example, if the blue part is like 0.3, for example, so it has an opacity of 0.3, for example, then we just have RGB 001 multiplied by 0.3, so 003. And we just add that with the contribution of the red layer, and then we just do the same thing. So essentially, this means that multiply together all of the previous layers in our alpha blending. Does this kind of make sense? I'm not sure if I'm over-explaining it or under-explaining it. But OK, let me know if you have any questions. OK, so the rendering part, naturally, in order to have this, so 3D Gaussian splats are just a bunch of numbers. So we have a bunch of positions, bunch of rotations, and we have these floating around in space. So these are not sorted. So you don't know, like when you have your array of positions, then it's not a sorted array, so you have no idea which one is in front of the other when you want to iterate through them in this for loop. So you need to do a global sort. So they end up doing a global sort, which is actually very cool because they come up with a very efficient way. So I actually invite you to read up on this, and you can even see the CUDA implementation. Something that's very cool is that they use a radix sort, a GPU implementation, to sort things globally. And previous methods, previous point-based methods actually really struggled with having to sort through these Gaussians or whatever primitive they were using for each pixel. Because if you think about it, if you'd have no fancy accelerated way of putting these in order, then it's actually a lot of work to actually sort through these, and you're kind of losing the whole benefit of this very efficient alpha blending concept, which is directly available on the GPU. So of course, like every single time in computer graphics, when we say that something is very quick, it's usually very quick because it has some non-programmable already implemented GPU component that just runs through everything. So that's usually why things are quick in computer graphics, I think, or at least like matrix multiplication, for example, and many other things. But alpha blending is definitely one of those things that has some static hardware implementation that's fixed in place and just runs mega quick. So anyways, so they do one single sorting pass, and then they do the whole projection part where they splat all of the Gaussians into view space with some depth that they already have access to from the sorting part. And then they just blend these together with alpha composite where they have some transparency for each Gaussian, and they have some 2D Gaussian which is described by the 2D covariance matrix and the 2D view space position. And each Gaussian also has, for our purpose, an RGB color, because by this point we actually translated the spherical harmonic coefficients into RGB colors, because we already knew the kind of the direction of our array and our camera. So that was the whole point. So at this point, we essentially have a 2D Gaussian with an RGB color with some opacity for each Gaussian. And this is the actually part, because it's not that simple. They do a lot of like these little tweaks that made them achieve like 100+ FPS. And actually, there's a really fun talk that I'm linking at the end from one of the authors of the original paper that describes kind of this historical overview of how they went from 5 FPS to 100 FPS. I think it's worth watching. It's a nice talk. But in any case, one of these things is splitting the image into 16 by 16 tiles. And something very cool is that they do the global sorting of the Gaussians once, and then they split up the image into 16 by 16 tiles, and then they parallelize the alpha blending part between each of these 16 by 16 tiles. And of course, because they dispatch these into different GPU processes, if a Gaussian is overlapping 2 of these tiles or multiple of these tiles, they simply instantiate those Gaussians in multiple tiles. So if some Gaussian is present in multiple tiles, then it's just being instantiated in all of these. And this is one of the funky. It's kind of very important to making it work, but it's not like the crux of why it's a cool method. And I think it's very funny with Gaussian splatting to kind of balance what's an implementation detail, which kind of makes it work and runs it at 100 FPS plus, and what's kind of the theoretical thing that we can bring over to our next concept. I think it's very interesting how the two plays together plays into each other in 3D Gaussian splatting. So right now, looking at our kind of pipeline, we described how we can initialize our points, what's the parametrization of our points, and given some camera position, we can project our 3D Gaussians into 2D view space, and then we just described how we can rasterize this process. And naturally, the coolest part is that this is all differentiable, because the construction of those matrices that we use to project are all differentiable with respect to our parametrization. So we essentially have some scale vector from which we construct some matrix, and it's very cool that we can differentiate through all of these steps that we mentioned before. And then now is the part to just look at some loss as compared to some image. Oh, yes, but before that, just a couple of notes about the optimization is that naturally we want to optimize all of these properties. So as I mentioned, we are optimizing the opacity for each Gaussian, the position, which is x, y, z, and then we have the covariance, where the sigma scale vector is a scale along each axis, so also 3 more numbers, and we have our quaternion, which is described by 4 numbers. And then we also have a view-dependent color from the spherical harmonic coefficients, which is 12 or so numbers. And then they use the very typical deep learning machinery. So they use the Adam optimizer, and it's a gradient descent based iterative stepping scheme, of course. And they implement their original paper in PyTorch, but they also write some custom CUDA kernels, which makes it all run very efficiently. This is actually something that's bugging me a lot, because pretty much all of the implementation that are out there have some custom CUDA kernels, which is very nice and makes it run very quickly, but it's just very impractical to just quickly try it out on your machine. And I have yet to find a good tiny 3D Gaussian splatting implementation, which is just which is a end-to-end pipeline of 3D Gaussian splatting, but without you having to kind of do the whole custom CUDA kernel plugin. But in any case, and then for the image loss, they actually use an L1 loss, but it could have been an L2 loss, but L1 loss works fine. And then they also have something called the structural similarity index measure, or SSIM, which is kind of supposed to measure how well an image, like how well 2 images align as perceived by humans, essentially. And this is kind of a heuristic-based loss function based on human perception. And as I mentioned previously, we might want to put more Gaussians at some places or less Gaussians at some places based on the density of our details. So in every n iterations of our optimization, we might be pruning Gaussians. We are pruning Gaussians, so taking away, erasing Gaussians. And we have, and they describe 2 heuristics for this. One of them is that if our transparency is smaller than some epsilon, so if it's tiny, so if it's almost completely transparent, then we just take it out, it doesn't contribute, and it's just a weird floating blob. Or if the Gaussian is too large and just simply it's just too big, and it's probably not meaningful, then we just take it out because it's probably not the right Gaussian that we would like to have. And then next to this pruning, which is taking out Gaussians, we might want to increase the number of points where necessary. I think they do every 400 iterations, but it's just a hyperparameter. So they have a densification in every n iterations. And this is yet another heuristic that they observe, that high positional gradient in view space, which means that if we have this Gaussian and we have our loss function, and we differentiate the loss function with respect to the position of this Gaussian, then that's the positional gradient. So if I tweak the position of my gradient, how much does that influence the loss? And you can also think of this if I tweak that little knob that I kind of started the lecture with. So if I tweak that knob, how much does that influence our resulting loss? And if this is high, then that means that tweaking this Gaussian and just putting it a bit further away actually results in a huge change in the loss function. So that means that this Gaussian is probably not at the right spot. And which means that the region is not well reconstructed yet. And here they kind of describe two possibilities here. We might be under reconstructing if we have some geometry and we have some Gaussian that's kind of not enough to cover. Like no matter how you tweak this single Gaussian, you cannot properly cover this whole geometry. So they end up cloning this Gaussian. So they end up actually cloning the Gaussian along its positional gradient, and they just put another Gaussian, and then they just continue the optimization, and hopefully it converges to nicely cover the geometry. And then the other thing that could happen is over reconstruction, where a single Gaussian covers too much geometry, and it would be nice to kind of fine scale that region, so that they actually split this bigger Gaussian into two smaller Gaussians, and then they just continue optimization, and hopefully it converges. But these are essentially heuristics which work well, but you could think up something just as nice, but this seems to work nice. And there is also another heuristic that they set the alpha transparency parameter to 0 of all Gaussians every 3,000 iterations, and this kind of helps them prune, because then the pruning part takes care of pruning out these Gaussians. Because ideally, if you set the transparency to 0, the Gaussians that actually matter, that we actually want to keep in our scene, will be taken care of by the optimization part. So essentially, those transparencies will be kind of tweaked back up by the time the pruning comes along. But if a Gaussian didn't actually matter and it was like weirdly like off at the side of the scene or something, it will just get pruned, and that's the way to get rid of some weirdly positioned Gaussians. Here are some qualitative results that at the time of publishing 3D Gaussian splatting, PSNR is also a human perception-based loss that they actually performed quite nicely on pair with the then best NeRF implementation, which was MIP-NeRF 360, but which is more important, that MIP-NeRF has 0.07 FPS as in that implementation, and 3D Gaussian splatting has a lot of FPS, like an unnecessary amount of FPS, which is a result of all of these amazing heuristics and GPU accelerated fanciness that we have going on. And yet another cool thing is that the training is not even comparable. So I think when they first implemented the 3D Gaussian splatting, they actually started out I don't know, like a day of optimizing or something, and then they just kept like every other week just halving it, and like doing this and this tweak in the GPU implementation. And the time of publication, it was much less. And actually, there exists some implementation that are even better. And something I mentioned before is that an isotropic Gaussian, which is kind of the same scale along each axis, results. So if they just had a single scale along each axis, then that would result in these little observable blobs. Or here you can see that these are not that nice. But if they let the Gaussians stretch into a full anisotropic Gaussian, anisotropy means that it's based on which angle you're looking at it from, then it has a nicer result. And kind of as a last thing, I just wanted to show you this very cool demo as we are wrapping up. They published something called 4D Gaussian splatting in a follow-up paper. And this is not from that paper. This is actually an industrial application where some company called Infinite Realities bought the software license to 3D Gaussian splatting and 4D Gaussian splatting. And what they are doing here is essentially something called spatial memories. And this is in real time. And I think it's just mind-blowing that you can make this work. And and here they are just documenting this memory for this family. I think just mind-blowing that this is like in this fidelity level, it's real time and runs reasonably okay on a if you have some GPU in your home computer, then you can just run this. And you can just move around this scene, and all novel views are actually reasonably nice looking. Novel view synthesis took a huge leap in recent years, and it's pretty much solved with some caveats, but it's pretty meaningfully amazing. Like just look at the And here I've just kind of collected a couple of next steps just to finish off the lecture. Of course, the homework assignment is a good way for you to kind of explore these things, hopefully in a enjoyable and very simplified way. And also, I'd really encourage you to read through the 3D Gaussian splatting paper, because I think it's a very nice read. And I think after this lecture, you will have a good enough understanding to kind of make sense of the missing parts. And actually, it's already kind of outdated, which is funny. But there is something called 2D Gaussian splatting, which actually splats something closer to surf holes. So essentially 2D Gaussian splats, And there are lots of heuristics and implementation details to going into how they parameterize those 2D Gaussians and how they project those 2D Gaussians. But there's a follow-up paper, which is splatting 2D Gaussians in 3D space. Not to be confused with splatting 2D Gaussians in an image space. That's what we are doing in homework. But 2D Gaussian splatting is splatting 2D Gaussians in 3D space. And there's also, as I mentioned, a very nice talk from 3 weeks ago, I think, from George Dratakis, who is a very, very amazing and professor who has done some fascinating work in the past many years. And he had a lecture series recently that kind of talks about the past, present, and future of 3D Gaussian splatting. And I think it's very well worth listening to, because it puts things very nicely into perspective if you care about computer graphics, computer vision, and kind of just hearing about all of these things. And I would really encourage you, and sorry, I'm going 2 minutes over time, but I'm almost done. I would really encourage you to just try all of this in action, because if you have a GPU at home, or even if you just hook it up with Google Colab or something, there's a Gsplat implementation, which is also part of NeRF Studio. And something very fun to try is to just take out your phone, go around your room, take some pictures, and train a Gaussian splat scene from that, or for that matter, a NeRF scene, and then you can even compare that. And it's a very nice implementation, which is very nice to run at home, and I would really encourage you to try that. And with all of that, thank you for your attention. And if you have any questions, I'm happy to answer any of them. Because I do have some backup slides that I can talk about, the little fun fact. Something I was afraid of putting in because I was afraid I would run out of time is something about Fourier embeddings. This is kind of like from the earlier sections of this presentation. Here we are just teaching a neural network to directly overfit for an image. So it's literally just learning XY pixel space into an RGB color. And if you remember this, I think this came up in the NeRF lecture, that we actually run our input coordinates, so XY coordinates, or in NeRF XYZ coordinates, into through some embedding space, which is called the Fourier embedding space, where they just map this lower dimensional XY or XYZ domain into a higher dimensional space, which is spanned by some sines and cosines, so essentially a Fourier space. And something very fun that when I did these little demos that I just did for fun, I actually thought that it would be just very easy and I just run it and it will fit. But actually it matters a lot like what embedding space you use. And this is a 512 by 512 image, and this is a 256 by 256 image. And I just wanted to mention it because I thought it was kind of fun. And I think this is what they used in the original NeRF paper, just a basic mapping of sines and cosines, whereas this embedding space is kind of feeding the input coordinates, so the XY or XYZ or whatever low dimensional space, into a higher dimensional space, spanned also by these sines and cosines, but kind of adding in this B matrix, which is randomly sampled Gaussian features with different Gaussian sigma values. And even if you just look at the initialization, so like what the network sees when it starts learning is actually quite different. And then you can see that this random Fourier space, this embedding space actually looks different. And it even struggles to properly learn a 256 by 256 or 512 by 512 image. And I think it's just very fun because this is yet another hyperparameter that makes sense to pay attention to when you train your NeRF at home or do whatever. And I think this touches on something very amazing about kind of computer graphics and scientific computing in general, that changing your space that you're working in actually makes a huge difference in any problem that you have. And I'm not sure if this will come up in these lectures, but I think the whole reduced dimensional embedding in some methods, kind of having a high dimensional space of like an image space and finding some meaningful low dimensional embedding parameters that can be used to reconstruct this high dimensional information, which can be a 3D Gaussian splatting scene, or which can be a whole image. This is kind of what you do in many existing neural network concepts, that you try to find a meaningful latent representation. But it's actually quite fun that this is actually the opposite where your neural network actually struggles to find meaningful patterns in this low-dimensional space. And you want to map this low-dimensional space into a high-dimensional space, which actually expands on the information available to the neural network. And instead of learning this space, because of course you could just say that, okay, I'm just putting in another layer of lots and lots of neurons, and this will kind of learn it. Actually, you can say that, hey, actually, this looks fun, and I can just fix this in place, and it will probably be quicker and probably more meaningful and more explainable if I just fix this, this high-dimensional embedding down. And I think this is just a very interesting thing to kind of think about, like kind of the dimensionality of what you're working with, and kind of how you can map different spaces to each other. Something that we were, of course, talking about in 3D Gaussian splatting was that the whole projection part. This is what we are doing here, essentially, that we are taking our 3D vert space, and this is staying in the same three-dimensional space, of course, when we apply the view transform, but we're essentially warping our space to align with our cameras, and then we once again project into another space that gives us these nicely oriented 2D planes. And I think just fascinating to think about how you can change your perspective. And the added extra part is kind of changing your dimensionality as well to make something work, which wouldn't work. Because actually for NeRF, it's not a trivial thing to just think up these Fourier features as embedding spaces to our neural networks. So I hope I didn't confuse everyone. Yeah, thank you so much for coming. And if you have any questions, I'm here to answer your questions. And yeah, or feel free to send me an email if you have any questions. And thank you. Or any public questions that, I don't know, might be interesting for everyone? Yes? Sorry, can you repeat? Yeah. Oh, yeah, that's a great question. So actually yes, that's exactly what and I actually think in the 4D Gaussian splatting paper, I wish I included that part. Actually, they have kind of a globe, kind of a capture room where they have cameras kind of taking just a blast of images, like all around the actors. And actually, it's a bit brute force. So I think there will come like many better ways of doing this. But what they do in 4D Gaussian splatting in the paper that they optimize for the first frame using the ground truth images all around the actors. And then they just step to the next frame, take the next set of images, and starting from those, so instead of reinitializing the Gaussian splats, they just use the end result from the previous frame to feed into the next, to start the initialization for the, to start the optimization of the next frame. And that's what they do for each frame, optimizing from the previous Gaussian splats. And this is actually something I would encourage you all to experiment with in your homework. That maybe you can find some. So this is actually from the homework assignment. So this is what you will be implementing. So actually, you can do the same thing. Oh, sorry. You can actually do the same thing with an image, essentially, that instead of using these randomly initialized Gaussians, you might think up some, like another image, for example. You could see how well it works, but that's essentially what 4D Gaussian splatting is doing. Or you can kind of warp. I don't know. You can play around with this. So yeah, does that answer the question? No time lag. Oh yeah, that's a great yeah. I think that's a great question, and I think that that's not the level of abstraction that they are working at here. So I don't think they mentioned that. I think that's a bit of a problem for the electrical engineers. So I think essentially they are just taking a video and they just align the videos essentially. So I think they essentially start from the capture set. So I think that's a different problem to set up that whole captured set. But yeah, I think that's a great question. And actually, I think if you just take multiple cameras, take videos, and you align the videos good enough, then I think it should work. Like I think that, or you can come with another method, look at some other method to kind of match those videos. Yeah, thank you. Great question. That's Okay, thank you. If no other questions, then thank you.